Hello student, welcome to our lesson today, lesson 3. In this lesson, we are going to look at latent heat of fusion. We start by looking at what it means when we talk of change of state. And just a reminder, you know that we have 3 states of matter. We have liquids, gases, and solids. So when a substance changes from solid to liquid, or from liquid to gas, or even the reverse, that is from gas to liquid or liquid to solid, then we say that this is change of state. And when it changes the state, there is either losing of heat or absorption of heat. Now let us look at effect of supplying heat on a solid. Now when we have that an ice is at negative 10 degrees Celsius and this ice is heated, the heat energy is used in raising its temperature to 0 degrees Celsius. So in other words, we are saying if you have ice at negative 10 degrees Celsius and then you supply heat, that heat energy is raising its temperature. The energy given to the ice at 0 degrees Celsius is used to change ice from solid to liquid, which implies that at this point, there will be no change in temperature. That is, the heat supplied to ice at 0 degrees does not change the temperature of the ice, but changes its state from solid to liquid. And that process, we call it melting. Now, that energy that is absorbed during the change of state, or that is lost during the change of state, is what we call the latent heat. And the term latent means hidden. And we are saying that it is hidden because we can't see the rise in temperature. That's why we are saying that it is hidden. Then from there, we can look at latent heat. We can define it as the amount of heat energy required to change the state of a substance without change in temperature. So in other words, we are saying latent heat can be either absorbed or given out. For instance, if it is during melting, then that latent heat is absorbed. But during the process of condensation or freezing, that heat is given out. That is, it is heat absorbed or given out during the change of state. That is what we call the latent heat. That is what we are saying. Ice at 0 degrees is converted to water at 0 degrees. Note that there is no change in temperature. So you have just melted, so the ice has changed into water, but that water is at 0 degrees. Therefore, there is no change in temperature. And therefore, that is what we are calling latent heat. From there, we can move to the latent heat of fusion. We have defined the word latent heat. But now when we talk of latent heat of fusion, we say that this is the amount of heat required to change the state of a substance from solid to liquid without change in temperature. Here we are specific. We don't just say that it is the change of state. We are saying that those substances are being converted from solid to liquid. Therefore, that heat energy that is required to change or to melt an object from solid to liquid, then that is what we call the latent heat of fusion. Note that when the liquid changes from solid, that is, we are changing now solid to liquid or liquid to solid. We have seen that during melting, that energy is absorbed. But during the condensation, that is liquid to solid, then that latent heat of fusion is given out. Let us explore the change of state of naphthalene using a cooling curve. Now, we first of all heat naphthalene to about 100 degrees Celsius. Then using the thermometer, we are supposed to check the temperature as the naphthalene changes its state. So during cooling, the temperature of naphthalene falls from about 90 degrees Celsius to about 80 degrees Celsius, where it remains constant. And at this particular temperature, all naphthalene gradually changes to solid, after which the temperature falls to room temperature. And this can be explained using a graph. We have the liquid naphthalene here. It's cooling. So OP represents the liquid cooling. And there is change in temperature. As you can see, the temperature is falling. But at point P and Q, there is no change in temperature, which implies that the amount of heat energy that is being supplied here or that is being lost the energy that is lost here is not changing the temperature, but all what is happening is that liquid is turning into solid. This is what we call now the melting point. Then from there, all the naphthalene now has turned into solid. And that now solid at point Q starts cooling, and it cools until it reaches the room temperature. So this is the cooling curve of naphthalene as shown in our explanation here. We have seen that the portion OP represents liquid naphthalene cooling, then PQ represents naphthalene changing to solid without change in temperature. That is why now PQ is just a horizontal line. There is no change in temperature. At that particular point, we are calling it freezing point, where the naphthalene is solidifying. In portion QR, solid naphthalene cools to room temperature at R. And during the period PQ, the liquid naphthalene is losing latent heat of fusion as it solidifies. We are calling it a freezing point because now the energy is being lost, and that energy is what we are calling the latent heat of fusion. Then from there we can look at specific latent heat of fusion. Remember now we have seen that latent heat of fusion is the energy required during the change of state from solid to liquid or from liquid to solid. That energy can either be absorbed or lost. But now when we come to specific latent heat of fusion, we refer to the quantity of heat required to change a unit mass. When we talk of a unit, we are talking of 1 kg mass of the substance from solid to liquid without change in temperature. So in here, when we talk of specific latent heat of fusion, it's that energy now, but it is changing a unit mass from solid to liquid without change in temperature, which implies that the specific latent heat of fusion is given by the amount of energy supplied divided by the mass. Therefore, Q, that is the amount of energy, will be mass multiplied by specific latent heat of fusion. So as you can see, the SI unit of the specific latent heat of fusion will be given by joules, because of the energy, divided by kg. So it is joules per kg. How do we determine the specific latent heat of fusion of ice? We have the arrangement here. We have the ice that is put inside warm water, and this warm water is inside a calorimeter. The calorimeter is highly lagged to ensure that there is no loss of energy to the surrounding. Then we have the Stala that is ensuring that we have a uniform temperature in this water. So this water is the one that is warming the ice, and the ice will melt. And remember, you have to take the thermometer reading. That is the temperature before and the temperature at the end. Then after getting all those readings, we say that the heat lost by the warm water is this one that was already inside the calorimeter, plus the heat lost by calorimeter is equals to the heat gained by ice, that is during the melting, ice at 0 degrees to water at 0 degrees during the process of melting, plus heat gained by the water or the melted water, that is water from 0 degrees to final temperature. So that way, because now this is where we have the specific latent heat of fusion, then we can use this one to get the specific latent heat of fusion. This is the method of mixtures. From there, we can look at an example. 1. Calculate the quantity of heat required to convert 50 grams of ice at 0 degrees to water at 0 degrees. We proceed as follows. Quantity of heat is given by mass times specific latent heat of fusion. But we are given the mass in grams, so we convert it into kg by dividing through by 1,000. And then we multiply by the specific latent heat of fusion, 3.4 times 10 to the power 5 joules per kg. When you multiply, you get that it is 17,000 joules. So this is the energy that is required to convert that mass of ice to water at 0 degrees. That is 17 kilojoules. Then question number 2. 32 grams of dry ice at 0 degrees Celsius was added to 200 grams of water at 25 degrees Celsius in a beaker of negligible heat capacity. When all ice had melted, the temperature of water was found to be 10 degrees Celsius. Calculate the specific latent heat of fusion of ice. Take specific heat capacity of water to be 4,000 joules per kg per Kelvin. We proceed as follows. We have seen that heat lost by warm water should be equal to heat gained by ice, that is ice at 0 degrees to water at 0 degrees. This is during the process of melting, plus heat gained by water from 0 degrees to a final temperature, and our final temperature is 10 degrees. So we have the mass of water, the specific heat capacity of water multiplied by the change in temperature. This must be equal to the mass of ice multiplied by specific latent heat of fusion, then plus the mass of water, then specific heat capacity of water multiplied by the change in temperature. Now, the mass of water is 200 grams. You convert that into kg, you get that it is 0.2. Then the specific heat capacity of water is given as 4,000, then multiplied by change in temperature. Remember, this was at 25 degrees and now the final is at 10. Therefore, it has lost some heat energy. So the change in temperature will be 25 minus 10, you get 15 degrees Celsius. Then you come to get the mass of ice, that is 32 divided by 1,000 to get 0.032 kilogram. Then multiplied by latent heat of fusion, specific latent heat of fusion, LF, then plus that ice or that melted water, 0.032, then multiplied by specific heat capacity of water, multiplied by the change in temperature. Remember, it was coming from 0 to the final temperature, so the change in temperature is 10 degrees. When you multiply all this, you get 1280, that is 1,280. This becomes 0.032 LF, and this becomes 12,000. Now, you take this on this side, you subtract to get 10,720. To get this, you divide it through by 0.032, and when you divide, you get that it is 335,000 joules per kg. That is now specific latent heat of fusion of ice. From there, we have the assignment. The assignment is testing what we have just covered. Make sure that you revisit the video, read again, discuss with your peers, and then come and attempt the assignment. So thank you, and let us meet in our next lesson.